So using hidden Markov models, there are three problems we are trying to understand. The first problem we try to understand is, given the parameters of the hidden Markov model, can we estimate the probability of seeing some observations? The second problem is, if we have the observations, can we guess the hidden states? And the third is, if we don't even have the parameters, we only have the observations, can we estimate the parameters of the hidden Markov model? Okay, so let's go to the first problem. And again, we're going to use the coin flip example to explain. So given all the parameters in a hidden Markov model, how do we compute the probability of certain observations? So in this case, supposedly we know the coin, we also know the transition probability and the emission probability. And we ask, what is the probability that we're going to see this string of coin flips? Okay, and to answer this question, there are a number of algorithms that have been developed. One is this forward procedure, the other is the backward procedure. So let's explain that. So this first problem is, we know the hidden Markov model parameters. We also know that we want to ask, what is the probability of seeing these coin flips? So this is the string of coin flips. Supposedly, we say, okay, if we know the coins that are used to flip these coins, what is that probability? Okay, you say that, okay, that's easier. So if we know that the first coin flip head is coming from a fair coin, then we say, okay, the probability of head from a fair coin is 0.5. That is the emission probability of a fair coin given a head. And the second one is, now the second one, we have a fair coin giving a tail, a biased coin giving a tail, fair coin giving a head, fair coin giving a head, biased coin giving a head, and biased coin giving a tail. And each of them is a emission probability, and you just multiply them together because they are independent. If we already know the coins that's used. Of course, it could have been coming from a different path, right? So if we switch these two coins, here is from a fair to a bias, and again, you will get a different probability, because now we're trying to use a biased coin to flip this head. And so here you can see the probability become 0.8. And again, in here also, we are trying to use a biased coin to flip this head, which is now 0.8. And so you calculate another probability. So you can imagine, for every given pass, there is a probability for observing this coin flip string of coins, right? So what is the overall probability of observing this? You can imagine. So then you ask, what is the probability of using this particular string of coins? And this one we know before. In order to use the first path, we first have to pick a fair coin, which is 0.4. Then we do the transition from a fair coin to a fair coin, 0.9, fair to a biased, 0.1, biased to fair, 0.3, fair to fair, 0.9, fair to bias, 0.1, and bias to bias, 0.7. So that's the probability of using this path of strings, right? The different coins strings. But if we decide to use another path, as we mentioned in here, we swap these two fair coin to bias coin, then you can see here, the first coin we picked will be an initial probability of using a biased coin, right? And then the rest is transition, transition, transition. But then the difference here is, instead of a fair to fair, which is 0.9, we're using a fair to biased, which is only 0.1. And so you can see that this will end in a different probability. And so every given path also has its own probability, right? So when we try to understand the total probability of observing a certain string of coin toss, we have to sum over all the possible paths. Remember, there are many different paths we can use, different coins we're going to use. And each path will have its own probability given the coins we use in that coin flip to give that particular coin toss probability. And so written out in overall is like this. So if we want to ask, given the parameters, what is the probability of seeing this coin flop is a summation of all the possible paths. First we ask, given the parameters, what is the chance that we're going to use this string of coins? And if we're going to use that string of coins, what is the probability that they give out those heads and tails, right? So you can imagine if we have to sum over all those different paths, it's going to take many computations. So for example, for a path of n number of coin flips, and if there are t number of hidden states, in our case, this is the length is 1, 2, 3, 4, 5, 6, 7. So 7 long, and the hidden states in this case we only have head and tail 2 states. There are 2 to the 7th possible paths. But you can imagine if we're looking at stock market, you easily go to a years of market price, 250 market days, and then to decide whether it's a bull or a bear market, this will be an unfeasible calculation. We can't possibly enumerate all the possible string combinations. And so in order to really solve this problem, we use something called dynamic programming. So dynamic programming is that we realize a lot of times we're trying to calculate this big matrix of numbers. Basically, this contains all the possible permutations of the paths. These are the states. And then from each of the states, we need to calculate the observed values. But we realize to get this whole permutation of all the paths is impossible. Therefore, we try to keep track of what result we got from the previous solution before we move to the next step, before we look at the next step in the path. And we try to keep track of the numbers and do the summations early on and use those numbers in the later numbers. This can help to speed up the current calculation by keeping track of the previous sub-problem solutions. So let's look at this from the coin flip example. So again, we have the observation that the coin is head, tail, tail, head, 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 tail. And there is a initialization, right? So the initialization is saying that what is the probability that I can use a head to see, I can use a fair coin to see the head versus a biased coin to see the head. So in this case, you can see if I'm using a fair coin in order to get this head, is first I have to pick a fair coin, and then from that fair coin I also have to give out a head, and that probability is 0.2. But if I have to start from using a biased coin, 0.6, and from the biased coin to get a head, it's much easier, then I get a higher probability. So the initialization is the probability of seeing this particular head from either a fair coin or a biased coin, right? So that's your initialization. Yeah, so you can see here, this number is the alpha 1 from fair coin, and then we do the bias. So So the yellow number here is the alpha numbers. If you want to understand what this red dot means, it's in order to see this coin flip and all the coin flips before, what is the probability that this is coming? For this coin, I'm using a fair coin or a bias coin. So let's look at, the first one is very easy. So let's look at the next step, okay? So we're trying to now calculate this alpha value for time, so this is time 1, now we're looking at time 2, okay? So we know at time 2 we're getting a tail now. So the alpha on this yellow dot on time 2 is asking, so and the top one is asking, what is the chance that I'm seeing a tail now and everything before it in order and use So now we look at time 2. We are asking that if we are now at time 2, in order to see a tail now, plus all the coin flips before that, what is the chance that I'm going to use a fair coin or a bias coin? So these are the yellow dots in here. So you ask, okay, if I'm going to use a fair coin in here, what do I have to do before? You say, okay, well, the previous coin can either be a fair coin or a bias coin. But if I use a fair coin, you can imagine I need to inherit the previous yellow dot, because I know this yellow dot means on the top means seeing ahead here and whatever before, right? And then from this probability from the fair, I also need to transition now to another fair coin. So it's this yellow dot multiplied by the transition probability from a fair to a fair. Now I'm using the fair coin. But the other probability is I inherit this yellow dot, which says if I'm using a bias coin to see the first head, right? And then I need to transition from a bias coin to a fair coin. And so I need to sum up these two probabilities in here. And now also because I'm using a fair coin, I need to flip the second coin, which is a tail. We need to do a transition probability in here in order to see that second tail, right? So that gives us the second probability. So let's do this calculation. So previously we have the alpha 1 and fair and alpha 1 bias, and now we are trying to calculate. You can see here from the previous fair coin, I'm now transitioning from fair to fair, plus if I use a bias coin before, I'm transitioning from a bias to a fair. So this is the probability of now using a fair coin now, and then we do a emission probability using this fair coin to give out a tail, which is 0.5. You get a new probability here. Alternatively, so this yellow dot is alpha 2. It means in order to see this coin flip as well as all the previous one, what is the likelihood that I'm using a fair coin in this second coin flip? And this is the probability. But then we can also look at the next, the bottom one. Also, there's a red dots in here. So you can see here, in order here to use a bias coin, I either previously use a fair coin, and then I transition from a fair to a bias, Or I can inherit this yellow dot in here, and then transition from a bias to a bias. And so that's now, this probability is now, I'm using the bias coin. But then from the bias coin, I also need to give out a head. And so I multiply that by the emission probability of giving a head from a bias coin. And so you multiply this probability together, you get a number. And so we can continue this process. And every time we try to calculate the new yellow dot, and that yellow dot means in order to see this particular coin flip as well as everything before, what is the probability I'm going to use a fair coin now? So you can see here, I inherit the previous yellow dots from fair coin, transition from a fair to fair, or I can inherit the previous bias coin yellow dot. Right, it's from here, and I transition from bias to fair, and so that's the probability of using the fair coin. But then from that fair coin, I also need to emit a tail, and so that's the emission probability. And so now I get the new alpha 3 being a fair coin. And then alternatively, I can say, okay, so I can use this yellow dot, previous coin being a fair coin, but transition to a biased. Or the previous coin could be a bias coin, and then I transition to I continue to use a bias coin. So this is the based on the transition probability. And then now that I'm in a bias coin, I also need to emit a tail from that bias coin. So this is the emission probability. And so now this gives me the number for the new yellow dot in here. And we can continue this process, right? In order to calculate the next yellow dot for alpha 4, it will be this yellow dot transition fair to fair plus this yellow dot transition from bias to fair. And then from this fair coin, I need to emit a head. And so that's the alpha 4 from a fair coin. Alternatively, we can do this. The alpha 3 fair, transition fair to bias. The alpha 3 bias, transition from bias to bias, I add them together. And now I'm using a bias coin, but from the bias coin, I need to give out a head, which is the emission probability. And so you can just keep going. Where is the end? Supposedly this chain just ends right here, but in reality we have 7. We just keep going. And so at the very end, we're asking, what is the probability of seeing a head at the end in this 4 position? Well, you say, okay, at the end there are only 2 probabilities. I see this head and everything before, either using a fair coin or using a bias coin. And so we add up these 2 probabilities, and that will be the solution to our problem. Yeah, so you can see at the very end, yeah, you say, okay, I'm seeing a head now, but when I add, so I'm seeing the head, and it either come from a fair coin or a bias coin. So I add these 2 numbers, and these numbers have already inherited all the previous numbers before to give me the probability of seeing head, tail, and everything before this coin, right? So that will give me a solution. That is the forward procedure. We can also solve it from backward. So that's the kind of interesting about hidden Markov model. We can solve it from forward. We can also solve it from backward. So backward is we also try to calculate some yellow dots, but now instead of calling them alpha, we call them beta. So the beta one is, if you think about it intuitively, what it means is, what is the probability of using this coin in order to see anything after it, but not including the current coin flip? So this initialization is kind of interesting. Initially, we actually don't do anything. We haven't, basically, you already see the last coin flip. There's nothing afterwards. You initialize each of them to 1. Okay, that's That's the initialization. But then we go backward to see the probability of seeing a certain flip after it using this current coin as being fair or bias coin. So remember, we already have so basically we're in the time t minus 1 in here. We are trying to ask, we try to estimate these two yellow dots in here. This one is, it means in order to see the coin flip after it, what is the chance that now I'm using a fair coin? So in order to estimate this yellow dot, I'm saying, okay, now I'm using a fair coin. But in order to see the coin flip after that, so there are two possibilities. One is I am using fair coin now, but the next one I'm going to use a fair coin. And from that fair coin, I give a tail, I flip a tail, and then I will and then from then on, I will inherit this yellow dot to get everything afterwards. And so that is the transition probability from a fair coin to a fair coin multiplied by the probability of the emission probability of seeing a tail from the fair coin, and then I inherit whatever is after, right? That's one way. The other way is, right now I'm using a fair coin, but the next coin I'm gonna use a bias coin. So you can see here it's a transition from a fair to a bias. Then from this bias coin, I emit a tail, and so that's the new yellow dot in here. So that's the transition probability, and from then on I can inherit whatever is after, right? And so that's the beta t minus 1 for fair coin. That's this dot. But if we want to estimate this yellow dot, which is what is the probability that at this time I'm going to use a biased coin in order to see all the coin flips after. So you say, okay, if I'm here using a biased coin, I can either do a bias to fair transition, and from that fair coin I'm going to emit the tail, and then from then on I will inherit this yellow dot. The other possibility is from this I just use bias coin transition to a bias coin. So that's the transition, and from this bias coin I emit a tail, and then I will inherit the yellow dot here to get all the things afterwards. So you can see every time we only need to look at one coin after, and then just inherit the yellow dot that we calculated at that step, because that yellow dot will already have summed over all the previous probabilities, right? And so this way we will get the beta for fair versus bias at the time minus 1. But if we have to keep going now at time point minus 2, we ask, okay, what is the chance that at this time I'm using a fair coin? You say, okay, from here I need to do a fair to fair transition, and from this fair coin I need to emit the head, and then after that I will just inherit whatever this yellow dot is that I calculated in the previous step. Or I can use this fair coin to go to a bias coin. Using that bias coin, I can also flip ahead, and then I will inherit this yellow dot to get all the previous numbers. And so you sum over this, right? So that's the new beta t minus 2 for fair coin. I can also do the same for the bias coin. If I'm using a bias coin in here, I could either transition from bias to fair, emit the head, inherit this yellow dot, or I can transition from bias to biased, emit the head, and then inherit the yellow dot from here, and I will sum them up, right? So now I calculate the beta t minus 2, and you can imagine at the end I keep going. In this case, in order to get this one, it's transition from fair to fair, emit the head and inherit this dot, plus transition from fair to bias, emit a head from bias coin and then inherit this yellow dot, and we sum them up. For this yellow dot, it's from biased to fair transition, from fair to head emission, and inherit here this yellow dot. Or we transition from bias to bias, then emit from the bias coin a head, and then inherit this yellow dot. Each of them is a multiplication, and then you add up the two possibilities. And you can imagine from this chain, we can keep going backward all the way, to the very end. How do we terminate in this case? You can see here, at the very, very end, we're asking, okay, we have to kind of sum up this last two. We're asking how to terminate. You say, okay, remember the beta is in order to see this coin, in order to see, if I use fair coin, the probability seeing all the coin flips after, or using a bias coin to see all the coin flips after. And so at the very, very end, in order to terminate, we say, okay, in order to see all the coin flips after, we have to either pick a fair coin and then give out that first coin flip, and then inherit the top yellow dot. Or we can use a bias coin, use that bias coin to make the first coin flip, then inherit the yellow dot from the bias coin side, and you add them up together. Actually, you can use both the forward procedure and the backward procedure to solve problem 1. And if you do this calculation well, you will see that the forward procedure and backward procedure should give you identical results. It should give you a same probability. And so that's problem 1. Again, here is we have the parameters for this hidden Markov model, and we're asking what is the probability of seeing a string of observations, right? Our goal is to sum over all the possible paths, and with each path calculates the probability of giving this particular observation. But since there are so many different possibilities of the paths, we can't possibly permute everything. We will try to do summations at every step and use the observation, the summations, the yellow dots at every step to help you calculate the numbers in the next step using dynamic programming. And so that will solve the first problem.